Hey everyone, welcome back. In today's explainer, we're going to dive headfirst into the invisible magic that powers our hyper-connected world. We rely on seamless data transfer for just about everything these days, but we rarely stop to think about the absolute monumental physics and engineering that make it all possible. Actually, think about it for a second. Whether you're streaming a flawless, high-def live feed from the International Space Station, using a quick GPS ping to navigate downtown, or honestly just swiping your credit card at some rural gas station where the transaction gets quietly routed through the sky, we take this invisible infrastructure totally for granted. So today, we're going to decode space communications and look at exactly how data travels from orbit down to Earth and back again. To really wrap our heads around the scale of what we're talking about here, just look at this number. 100 billion. That is the staggering factor by which a terrestrial signal's power drops before it even reaches a geosynchronous satellite. Imagine standing right next to a super powerful commercial transmitter on Earth. By the time that electromagnetic wave travels 22,000 miles out into the literal vacuum of space, its power is 100 billion times weaker. It's just an unfathomable drop in energy. So that brings up a massive and pretty provocative engineering puzzle. How does a signal survive that journey? How does human data traverse the vast, completely unforgiving expanse of space, overcome all this complex terrestrial interference, and still arrive perfectly intact? Well, by the end of this explainer, you're going to know exactly how communications engineers design these wildly sophisticated systems to pull off this impossible feat every single second of the day. Here is our roadmap for today. We'll look at the macro level with the Space Communications Network, move on to the 3 types of missions, look at the physics of the link, and wrap up with balancing the link budget. Okay, let's dive into this with our first section, the Space Communications Network. Before an engineer even picks up a soldering iron or bolts together a satellite chassis, they have to define the Space Mission Communications Architecture. Basically, this is the topology, the big picture layout for the whole network. It dictates the required data rates and the physical connections between all the major nodes. And these nodes, they're the fundamental macro structure of every single space communication system out there. We're talking about the multi-million-dollar satellites floating up there in the vacuum, the massive gateway ground terminals with those giant dish antennas that tie back into our terrestrial fiber optics, and, of course, the end-user terminals right here on the ground. Designing this network is a monumental task, and engineers actually follow a really rigorous step-by-step process to pull it off. They start with strict requirements. They absolutely have to nail down the exact coverage areas and precise data rates before doing anything else. Then they identify treatable elements. This is kind of the fun part where engineers get to be creative. They can play around, adjust antenna types, swap out repeater designs, or even shift frequency bands. Once they've got those puzzle pieces, they synthesize candidate architectures, essentially mocking up different solutions to see what sticks. After that, they relentlessly assess those mock-ups for compliance against their original strict requirements. Finally, they rank the best ones, pick a winner, and iterate. It's just a continuous dynamic loop of problem solving to optimize how these massive orbital networks function. All right, moving on to section 2, 3 types of missions. So there's this really fascinating contrast between the 2 foundational mission types, FSS and BSS. Fixed Satellite Service, or FSS, is all about symmetric, two-way traffic between large, fixed coverage areas. You can think of it like a massive two-way phone call between huge, highly sensitive ground stations. Because those ground stations are so incredibly capable, the satellite's payload architecture can actually be kept pretty simple. But then you have Broadcast Satellite Service, or BSS. This one is highly asymmetric. It's delivering heavy data in one direction straight to small, fixed user terminals, like that digital dish you see mounted on the side of a house. So if FSS is a balanced two-way conversation between equals, BSS is basically like someone grabbing a giant megaphone to shout high-power broadcasts out to a massive crowd. And then we have our third commercial category, Mobile Satellite Service, or MSS. This provides symmetric two-way communication directly to what engineers call disadvantaged mobile user terminals, like a handheld satellite phone or a tiny terminal on a moving truck. Because those user devices have incredibly small antennas and super low transmit power, trying to pick up their return signals from space, well, it's like trying to have a delicate two-way conversation in a crowded, exceptionally noisy room. To actually make it work, MSS satellites need incredibly sensitive receivers. It's absolutely awe-inspiring when you realize that an antenna sitting 22,000 miles away in orbit is engineered precisely enough to hear the faint whisper of a tiny handheld device down on Earth. They use highly directive, overlapping spot beams just to catch those faint return signals. Okay, time to transition from the macro network down to the micro level. In Section 3, the physics of the link. What's really interesting about this is how the invisible electromagnetic spectrum is carved up by regulators into distinct operating bands, like L, S, C, X, K, U, and K bands, all operating at different gigahertz frequencies. You really have to think of this spectrum exactly like highly sought-after real estate. You can't just transmit anywhere you want, right? National bodies like the FCC and international ones like the ITU strictly regulate this territory to make sure users don't drown each other out with interference. Your mission's assigned band is going to fundamentally dictate your payload architecture. But because that spectral real estate is so tightly constrained, engineers have to get exceptionally creative. They use a brilliant trick called polarization. This is basically the spatial alignment of the wave's electric field. It can be linear, meaning it ripples vertically or horizontally, or it can be circular, literally spinning right-handed or left-handed as it travels through space. By isolating these orthogonal signals from one another, engineers can transmit two entirely different streams of heavy data on the exact same frequency without them ever interfering. It is such an elegant physical workaround. They are literally doubling the available bandwidth just by twisting the wave. But of course, this spectral real estate comes with a catch because physics provides some pretty serious natural enemies to our signal. As a transmission travels, it faces an absolute gauntlet. The universe essentially wants our data dead. First, you have free space geometric dispersion, which just means the signal spreads out and drastically weakens over sheer distance. But then it hits our atmosphere. Water vapor absorbs signals peaking around 22 gigahertz. Molecular oxygen creates massive signal attenuation at 60 gigahertz. Heavy precipitation, like a local rainstorm or wet snow, physically absorbs and scatters your data. And finally, you get scintillation, which causes rapid variations in the refractive index of the atmosphere, making the signal rapidly fluctuate. So yeah, rain, gases, and simple distance are constantly conspiring against your link. So to manage these massive, continuous drops in power, engineers rely on a very specific mathematical tool, the decibel, or dB. Now, I know that sounds a bit intimidating, but let's totally demystify it. The decibel is simply a base 10 logarithmic unit that describes a ratio. Remember that crazy 100 billion factor we discussed right at the beginning? Yeah, nobody wants to do math by multiplying and dividing billions and trillions all day long. The decibel is literally just an engineer's mathematical shortcut. It turns those massive, unmanageable exponential drops into simple, small numbers that you can easily add and subtract. It is an absolute lifesaver that keeps the math super clean for the people designing these systems. Which brings us to Section 4, balancing the link budget. So how do engineers actually prove that a signal will survive the journey? Here is the master equation, and it's beautifully simple. The power at the receiver equals the transmitter power multiplied by the transmit antenna gain multiplied by the receive antenna gain multiplied by the losses. This brilliantly illustrates how all the complex, chaotic physics we just discussed coalesce into basically one master accountant's ledger. Every single watt of power, every tiny boost from a shaped antenna, and every bit of atmospheric loss is strictly accounted for right here in this one line. Let's break down this highly technical math by comparing it directly to something we all know, a bank account. Think of the transmitter's raw power and the amplifying gain of the antennas as your income. This is the positive signal strength you're depositing into the link. On the flip side, the geometric free space loss, the massive atmospheric taxes from that rainstorm and oxygen we mentioned earlier, any antenna pointing errors, and even the thermal noise inside the receiver itself, those are your expenses. And just like your personal finances, to make the communication link viable and avoid bouncing the check, your income absolutely has to exceed your expenses. So the crucial point is the ultimate bottom line, the link margin. This is the difference between the actual power-to-noise ratio you deliver and the absolute minimum threshold required by your digital modulation scheme to effectively close the link. If this margin is negative, your signal goes bankrupt. The data gets completely swallowed by background noise, and the communication link drops dead. That's why engineers purposefully design networks with a positive link margin to give the system a buffer. It acts exactly like a financial rainy day fund, literally protecting the data against unexpected expenses, like a sudden heavy thunderstorm rolling over a ground terminal. We've journeyed all the way from these massive macro-orbital network topologies down to the delicate logarithmic math of the link budget. The careful, relentless balancing of transmitter power against the sprawling vacuum of space and Earth's totally unpredictable weather is just a true modern engineering marvel. But let's leave off with this provocative thought. As our networks push further and further into deep space, establishing permanent presences on the moon, targeting Mars, and looking even beyond, those free space expenses are going to grow astronomically. So what new currencies, what new technologies, undiscovered spectrum bands, or crazy quantum coding tricks are we going to need to balance the ultimate cosmic link budget? It's a wildly fascinating frontier for the future of space exploration. Thank you so much for joining me for this explainer. Stay focused, and I will see you next time.